Lights, camera, action. There is an actual scientific purpose for this thing, which we'll get to in a minute. Today's lesson is bending moment. Now, last week we did the second moment of area, which was a preparation towards doing bending stress. This is the second step in that preparation. The other thing we need to know before we can work out bending stress is the bending moment. Bending moment is our substitute for force. I'm going to go back to the original stress formula that we had right at the beginning for axial stress or shear stress, which is simply stress equals force divided by area. Our substitutes in bending are these. Instead of area, we have second moment of area, and instead of force, we have bending moment. And that's almost the formula. The formula actually is another one in here, my over I. So that's in bending, and this is simple. Bending stress, simple stress. So you can see there's similarities between I and A. That's an area number, and the M is related to the force. It's what are we doing to the beam? How much force is being applied to the beam? All right, now what is a bending moment? A force is applied to the beam and it's causing the beam to bend down. The beam has to resist that force by bending back again, all right, which is the job that this spring's doing. It's replying to that force by rotating back. Now, what's it actually doing? The force causes it to go downwards, like this. So the section of the beam has to push the left-hand side downwards, right, in this direction. So it's doing anti-clockwise. The force here is causing this beam to go down, so the beam has to react by trying to make that one go down that way. So the section of the beam has to rotate the right-hand side clockwise and has to rotate the left-hand side anti-clockwise. That is called bending moment. Rotating both sides downwards in order for this not to break. The higher the bending moment, the more likely this is to break. So in this example, we have a moment applied to the left-hand side by the cross-section. So we're referring to a cross-section in the beam. Now there's a slight problem, and that is if I asked you, what is the bending moment right there in the centre of the beam, you've got two answers. You could say, oh, it's trying to do this to that side, or it's trying to do this to that side, and they're equal and opposite. And if you add those two moments together, we already know that if you add all the moments of something in equilibrium, they add up to 0. And if I took a cross-section of the beam, if I added all the moments on that beam, it's trying to rotate one side clockwise, the other side anti-clockwise. If I add those two together, I get 0. So how can I give an answer for the bending moment here? Well, it's a little bit like force and stress. With force, remember, we had two forces, one left and one right, or one up and one down, and the stress was defined as that force divided by area. Well, it's the same with bending moment. I have a left one and a right one, or a positive and a negative, but when I'm asked for what is the bending moment, you only have to apply one of them. So how do we know which one? Is it the plus or the minus? How do we decide which one's positive, which one's negative? We're going to treat anything that causes sagging as a positive bending moment. Anything that causes hogging, that way, that's called negative bending moment. Hogging, negative, sagging, positive. So we don't worry about what's left or right-hand side. We just say if it's doing a sag, that's a positive bending moment. If it's doing a hog, that's a negative bending moment. Now, how do we actually calculate the bending moment? It's actually really simple. All we have to do is take half of the beam and do a moments out from the centre. I've got a beam. It has, very simple, it's 6 metres long, 3 metres on each side. I'm asking for the bending moment in the centre. Obviously, that's where the bending moment is going to be maximum, right in the middle. If that was to break, it's going to break in the middle because it breaks due to bending moment. I have 12 kilonewtons in the middle, and from our forces subject, we have to do equilibrium. It means we need 6 kilonewtons on either side. So you need to do equilibrium first before you do bending moment. Right, so the original question looks like this. And you're asked, what is the maximum bending moment for this beam? Well, we decide to take a cross-section through there because we can easily see that that's where the maximum bending moment will be, in the middle. If I do that, I then do a free body diagram of either side. It doesn't matter which side, so let's say I take the left-hand side. That's my diagram, and then I have something here which is applying a force, implying a moment to this section in order to hold it still, because this thing is supposed to be in equilibrium regardless of what free body diagram I take. So if I chop half of the beam off, I need to be able to hold that with a bending moment here that stops it from rotating. Now that bending moment is quite easy to calculate because I take a moment from the centre. Let's call that A. Moment at A is force times distance. Force is 6 kilonewtons and the distance there was 3 metres. Now what are the units here? We have 6 kilonewtons and 3 metres, so that will be kilonewton metres. We just calculated the maximum bending moment for this beam to be 18,000 newton metres. If I took the other side, I would get exactly the same calculation. We've got 6 times 3 equals 18. Now how do I know if this is positive or negative? Because if I do this one, I get it's rotating anti-clockwise, so that should have been a minus, shouldn't it? And if I do that side, I get a positive. So one's plus, one's minus. What do? Forget that. How do we decide plus and minus? By a smiley beam is positive. Right, if the beam is sagging, that's positive bending moment. So is this one positive or negative bending moment here? Positive. So M equals positive 18.
This should be negative. It's anti-clockwise.
Negative is that.
That bending moment?
No, it's not. It's not exactly the same as moment, because if I take the moment on that side, yes, that should be negative. Correct. So that bending moment there is minus. Yes. If I took the right-hand side instead, I'll get positive. So I get positive 18 there, negative 18 there. And we've now got a quandary. Which one do I take? Well, they've already worked that out. Don't worry about that. You can pick whichever side you like, whichever's the easiest probably. But you don't make a decision about plus and minus until you go back to the beam and say, sagging, that's positive, hogging, that's negative. Because bending moment is actually a decision that you make. It's the same as forces. Remember, you have two forces, one up and one down. You could say, oh, that's positive F and that's negative F. But when you work out stress, you just say, what is the force? You don't add the two forces or decide that way. So we decide tension and compression by whether they're pulling or pushing. Well, we decide positive or negative bending moment because we will always have a plus and a minus, so we have to decide by sagging or hogging. That's the only option.
Like semi-trailers, like just tabletop semi-trailers, they build them with a positive bow, they call it, right? Because when they load it up, they come down.
Yep, and bridges too. They build a bridge with a slight positive bow because the concrete begins to creep and begins to flatten out. If they build it dead straight, 10 years later people say, oh, that's sagging, I'm not going on there.
That's unusual.
Well, that's all you need. So you can do any sort of questions. The only problem is, what if I gave you a question that was a bit more complicated? In this question, it was very easy to choose a point to take the bending moment because it's obvious to us that the maximum bending moment will be in the middle, where the force was applied. That's obvious. What about if I gave you one like this? Where's the maximum bending moment? Whoa, not so easy now. Especially if we don't know what all those numbers could be all over the place too. You know, this is 20 kilonewtons per metre. Yeah, so where is the maximum bending moment is not obvious anymore. So we have another technique that we need for plotting the bending moment. We could, if we knew where it was, if somebody said, find out the bending moment for me just there please, then we can do that simply. We can cut the beam in half and do the moments on whichever's the easiest side, and then work out the bending moment, have a look at it. If it's positive on one side, negative on the other, you know it's a positive bending moment, like this. So if it's negative on the left, positive on the right, that'll be positive bending moment, or the opposite way will be negative. So you can work it out, but if they ask you, what is the maximum somewhere on this beam, It's not so simple. You'd have to go running around taking every single point, and when you have a distributed load, you don't even know where it is in the distributed load. You'd have to go all the way through. So what do we do in that situation? Well, there's a second technique for calculating the bending moment. Right, now this other technique uses a completely different method, and it goes through a thing called the shear force. A shear force is the sliding effect inside a beam. It tends to happen more if you had a very short beam. So if the beam was extremely short and had a very large load on it, instead of failing in bending, it can actually fail in shear just by sliding. So bending is more an issue for a long beam, and shear is more an issue for a short beam. But we're going to plot the shear along the beam first and then use shear to calculate bending moment. Alright, so what does shear mean? Imagine if you had a beam made out of a bunch of magnets that were lubricated. They were slippery, but they stuck together. So when you push down or push up on the beam, instead of the beam bending, the beam slides. Right? So just imagine that. So we're not going to worry about whether it does this or not. We're only going to worry about whether it goes up or down. It's not allowed to bend, only slide. So we're focusing on only one thing, on shear. We also have a definition for positive and negative. Again, just like we did with bending, positive shear force means it goes up on the left-hand side, down on the right. So that would be an indication of positive shear force, because we need a plus and minus. All right. Now, how this works is best described in an example. Back to that simple one again. Right, this time I'm going to plot the bending moment all the way along the beam. Now, we've done this already in this diagram by taking cross-sections every metre along the beam. If I was to cut the beam 1 metre along, just here, then the bending moment on the left-hand side is 6 times 1, which would be 6. So if I was to plot bending moment here, this is my free body diagram. This is my bending moment diagram. At the end of the beam, there's no bending at all because it's connected to the air. You can't have bending when it's a blank end. So you always know when you have a free end, then that the bending moment must be 0. So I can put a 0 here and a 0 here. If I go 1 metre along, if I was to cut the beam at 1 metre, I'll have 6 kilonewtons times 1 metre. So what's 6 times 1? That'll be 6 here. Go 2 metres, it'll be 2 times 6 is 12. And 3 metres, 18. If I was to pick any point between those, I can measure it off the graph, what our bending moment is. So this is a diagram of the bending moment all the way along the beam. And it's positive because I know it's a sagging bending moment. Now, if I was to cut it here, if you look at the left-hand side now, it looks like this. 6, 12, and I'm cutting here, taking my moment. If I take moments from here, moment is 12 times 1. So moment at A equals 12 times 1. Is that positive or negative? It's negative. And this is 6 times 4. That's positive. So I got minus 12 and 24, so I end up equals positive 12. And likewise, if I go 1 more metre, I'll get positive 6. So starting from the left-hand side, I worked my way cutting the beam all the way through and ended up drawing a graph of the bending moment. And that's the sort of thing that we want. Now, this one was easy to predict, the maximum, because we knew it was going to occur in the centre of the beam. But if we do the same technique for a more complicated beam, we'll have a graph, and wherever the maximum is on this graph will be the calculation that we're trying to do. Now I'm going to show you a different technique for arriving at this same answer through the shear force diagram. So that's the first principles method, doing a cross-section of the beam, cutting the beam. Now I'm going to use the shear force diagram method. Right, now the shear force diagram has only one rule, and that is if it's up on the left-hand side, it's positive. So a positive shear force means the left-hand side goes up, the right-hand side goes down. Right, how much shear force do I have in the end? There's nothing because it's a blank, so I can start my shear force at 0, and I should end up at 0 here over this side. If I was to cut anywhere between here and here, no matter where I slice it, the left-hand side will always go up by 6. Because how much is the left-hand side being pushed up? 6 kilonewtons. I have 6 kilonewtons on the left-hand side, and it's trying to push it upwards. So the shear force diagram is 6 everywhere. At any point, it's 6. So the graph looks like this. Now, if I was to cut anywhere on the right-hand side, anywhere through here, the left-hand side is going up by 6 and down by 12. So what's the total on the left-hand side? It's now down. So this would be a negative shear force. Minus 6 all the way. And that's my shear force diagram. Now, these are actually quite easy to plot because what you do is you start on the left-hand side with a free end, and you just, wherever you see 6 going up, you could just go up. You see 12 going down, you just go down by 12. And then when you get to the end, hopefully, you should get back to 0, which we do. If we minus 6, we go up by 6, we're back at 0. So it's almost just like keeping track of the forces as they're applied. Makes them very quick to draw. Now we have a little rule, which is converting a shear force diagram into a bending moment diagram. Works like this. The height of the bending moment equals the area under the shear force diagram. In fact, what we're doing here is a little bit of calculus. We're integrating this curve to get our shear force diagram. It's the same as like velocity accelerations and things. The distance is the area under the velocity graph. All right, so let's see how this works. We'll go 1 metre at a time. After I've done 1 metre, what's the area in here? It's 6 times 1, which is 6. So what's the area in the whole rectangle here? 6 times 3. So the area is 18. So this area in here is 18. So when I plot that point there, the plot is at 18. And the area in here is now negative, so I take away 6, take away 12, take away 18. So down, back down to 0. Now it kind of makes sense really, because moment is distance times height, and distance times height is also area. So that's why, no, it's obvious that's why moment is the same as area, because it's length times height. But the advantage of this method is that shear force diagrams are much easier to draw than bending moment diagrams. So you draw them up quickly, and then you can just track the areas. And the nice part about it is you know the maximum will be when all of your positives are used up and you're starting to go negative. That's when you're starting to take it away. So you only need to calculate the area of the positive part. And then you've got your positive bending moment. All right, so the point of that, though, is you do it for a complex one. If it's a simple one, like a simply supported beam such as that, and you know where the bending moment is, or if you're asked to find the bending moment at a particular point, you only have to section the beam and do bending moment for one side of the beam. If you don't know where it is, you'll need to do a shear force diagram and then perform this bending moment diagram to find where the maximum is. Let's have a look at a more complicated example. Here's one where we have 2 forces applied this time. And so when we draw the shear force diagram, it goes up by 3, goes along, nothing changes, no applied forces, so the shear force remains the same, until we have down by 3, which takes us to a 0 shear force through here, which is fine. And then we have minus 3, so we end up like that. And when we take the areas, we add up the area here, 3 by 1 is 3. Then there's no change of area, so that remains the same bending moment along here. And then we go down again. Okay, a little bit more complex this time. We have 1 force down and 1 force up. So our shear force is 11. We need to do these reaction forces first. We can't move until we've done all the reaction forces fully completed. Then we can start our stresses. So up by 11, nothing happens for 2 metres, so that stays a constant. Now it goes down by 19, so from 11 down to -8. Nothing happens for another 2 metres. Then we go up by 5, takes us to -3. Nothing happens for the last 2 metres. Then 3 takes us back to 0. So our shear force diagram looks like this. When we go to draw the bending moment diagram, area in here, 11 times 2, 22 kilonewton metres. Now we've lost some area, which is 8 times 2, which is 16. So subtract 16 off 22, we end up, so now we're at 6. And that last 2 times 3 takes the 6 down to 0, because that's negative. And where's our maximum bending moment? Right there. Now, one type of beam we haven't looked at yet is a cantilever. Cantilever is only supported on one side instead of supports on both sides. Whenever you have a cantilever, the best thing to do is to set it up so that the free end is on the left-hand side, because it's much easier if we just keep working from the left to the right-hand side each time. There's no rule that says you can't just switch it around. I'm going to make this side the free end, because when I have a free end, I know the bending moment is 0 there. So I start with my shear force diagram. It's going down on the left-hand side for that first section here, so it's going -4, and that continues for 2 metres. Then it goes up by 9, so it's down by 4, up by 9, so altogether from here to here, the shear force is 5. So I go from -4 up to 5. So I have a constant shear force of 5 kilonewtons all the way until I hit this next one. I hit the 5, I've now got 0 shear force until I hit the wall. So no shear force between there and there. Now, just because you've got no shear force doesn't mean you don't have bending. All right, now we go to do the bending moment diagram. This is a good example of where you really need to do one of these diagrams so you know where the maximum is. 0 bending here. And what's the area in here? It's 4 times 2, which is -8. So I'll go down to -8. What's negative bending moment mean? It means hogging. So that means the shape of the beam here is downwards, curved downwards. Now, what's my next point? My next point will be over here. So I've got 5 times 4, so that's 20. The area in there is 20. The area in here was -8 plus 20. So now I'm going to go to positive 12. So the bending moment at this point is positive 12. And then there's no change of area. There's no more shear force across here. So that positive 12 stays the same all the way until we hit the wall, which means that it doesn't go back to 0. So the wall itself has to have a bending moment to hold the beam still. So the support at the cantilever will be 12 kilonewton meters to balance this one. Where's the maximum bending moment? The maximum bending moment is anywhere between the 5 and the wall. Not necessarily on the wall, but anywhere in between. It's a slightly unusual setup because we've got equal forces up and down here. But we do have maximum bending moment starting at the 5 and all the way to the 12. Anywhere there has maximum bending moment. Or we might be asked what's the maximum negative bending moment, because the beam might be set up to be better one way than the other. For example, a beam like this, it might prefer to be bending this way rather than this way. And so we may be interested in what's the maximum negative bending moment as well. We can double check this by cutting the beam anywhere at all and making sure we're getting the same answer as we have here. Just another example, we'll run through this one fairly quickly. We're drawing -2 down here, goes for 1 metre, go up by 10, down by 20, up by 20, down by 10, up by 2. And hopefully you get back to 0 here. So it's quite easy to self-check, because you should be getting back to 0 on a free end. If it was a cantilever end, not necessarily back to 0, because it depends on the force. But free ends should have 0 shear force on both ends and 0 bending moment on both ends. You can't apply a bending moment to the air. All right, now I'm going to do a bending moment diagram based on the sum of the areas in the shear force diagram. So these are all 1 metre apart, so the area in here is -2, so I go from 0 down to -2. Now I've got 8 times 1, so I'm going to go up by 8, which takes me up to 6. This area in here is -12, so it's 12 times 1, so starting from 6, go down by 12, so now I'm -6. Up by 8 again, which takes me to 2. -2 takes me back to 0. Where's the maximum bending moment? Well, The maximum positive bending moment is there, which is under the 20. The maximum negative bending moment is there, on top of that 20. So this one's hogging the strongest, this one's sagging the strongest. Alright, now the worst ones are the ones that have a distributed load on it. We've worked with point forces. What happens when you have a force that's a uniform loading along part of the beam? Simply supported beam, distributed load there, and a force here. We're going to start on a free end and draw our shear force diagram. Okay, so 17, it's up on the left hand side, that's positive 17. Nothing happens for 3 meters. Fine so far. Then we go down by 12, so it goes from 17 down to 5. Nothing happens for 2 meters. Good. We're up to there. Now what? We have a distributed load. Now a distributed load is a certain number of newtons per meter. And this one is 4 kilonewtons every meter. That means every time I go along 1 meter, it goes down by 4 kilonewtons. In this case, we are not allowed to multiply my distributed load across and put one force in the middle. You're allowed to do that to find my reaction forces, but you're not allowed to do it when you're doing stresses. It's not the same. So I have to obey 4 kilonewtons every meter. So what you can do is just think in terms of 1 meter at a time and go, okay, well it's supposed to go down by 4 every meter. So I'm starting at 5, so after 1 meter I'm down to 1. Then minus 3, minus 7, minus 11, minus 15, until I get down to minus 19 here after 6 meters. 6 fours are 24, 5 minus 24 is negative 19. You'll notice what happens with a distributed load is you get a slopey line. All the other forces are horizontal lines in between, but when you have a distributed load, you get a sloping line. And the slope of the line is the distributed load's 4 kilonewtons every meter. So that's actually the slope is 4 per meter. Minus 19, and fortunately our reaction force on the right hand side is 19, so that takes us back to 0. So that shear force diagram looks correct because we got to 0 at the end, which is what we want. Now we have to draw a bending moment diagram. Alright, the area in the first part is 17 times 3 is 51, so we've got straight up to 51 in a straight line. That's nice and simple. Now we add a little bit more area in here, which is 5 times 2, which is 10, so we go from 51 to 61. So far so good. Now, when we integrate the area under a straight line on an angle, we produce a parabola. And that's a bit of a pain to plot. When we do a parabola plot, we usually just need 3 points and then just rough it. But what are we really after here? The thing that we really want to know is the maximum. And we don't know where the maximum is. The maximum is when all of this area has been added up, because once we start subtracting area, it's going down again. So we only need to know what is the area in that little shape there, which isn't too hard. So if I can calculate that area, I have my maximum bending moment. So don't freak out too much about parabolas in our bending moment diagram, because all we really need to know is the area in here. If I can calculate that area, I've got my maximum point on the parabola. I've already got my start point here at 61. I already know the end point down here will be 19 from the bottom, because that's what happens in this area here is 1 times 19. So I can get that point, and I'm after the maximum anyway. So 3 points, and then you can just draw a freehand curve through the as a parabola through those 3 points. So we need to calculate this area in here. So if I zoom up on that section, this is 5, and after 1 meter I've gone down by 4. So the distance along here is 1.25. So I can then calculate the area of this triangle here, which is that triangle. If I got the area of that triangle, I add it to 61. That'll give me my answer. What's the area here? It's 5 times 1.25 divided by 2, which gives me an area of 3.125. Add that to 61, I get 64.125. That's my answer. The bending moment is the area in the shear force diagram that's positive. Or I could have done it the other way. I could have worked out the area in here, because they need to balance. And I would have got 64.125. Right, well that's about as bad as they get when you have a distributed load. You'll be making a straight line instead of a horizontal line. You make a line on an angle in the shear force diagram, which creates a parabola in the bending moment diagram. Two different ways to load a beam up. I can load up the beam by putting all the weight in the middle, or I can load up the beam by spreading the weight over the whole length of the beam. I've added 20 kilonewtons, or I've done 2 kilonewtons per metre for 10 metres, which is also 20 kilonewtons. So the reactions are 10, 10 on the left, 10 on the right. Shear force diagram, 10, nothing happens, 20, nothing happens, 0. Positive, negative. Bending moment diagram, 0. So that's 5 times 10 gives me 50, and this is negative 50 back to 0. Right, so my maximum bending moment is 50 kilonewton meters. Is that positive or negative? Being pushed from the top, that's positive. It come up positive in my graph anyway, so that's a positive there. Positive bending moment, sagging. All right, now let me draw this one. All right, we're going up by 10, exactly the same as last time. For every metre I go down by 2, so at 1 metre it's now 8, 6, 4, 2, 0, minus, and end up with this. That's my shear force diagram when it's a distributed load. So let me calculate the area under this section here. It's 10 times 5, which is 50, but it's a triangle, so it's 50 divided by 2. So it only goes up to 25. Now if I was to plot every metre, I would plot myself a parabola, if I want 1 metre at a time. So if you want to draw a nicer parabola, you can plot some extra points in there, but that curve only comes up to 25 kilonewton meters. So which is better, to put all the weight in the middle of the beam or to spread the weight over the length of the beam? It's better to spread it out, isn't it? By spreading the weight over the length of the beam, it's only half the bending moment. Or you can put twice as much weight on compared to putting all the weight in the centre. Let me just recap. Bending moment is how much the beam wants to break, and it represents how much the beam is rotating each side down in order to hold itself still. Bending moments are easy to calculate because all we have to do is slice the beam exactly where we want to calculate bending moment and do the calculation for one side of the beam. What are the forces on this side of the beam? And resist all those forces by rotating here to hold it still. Or if we want to pick the other side, we can do the same thing for the other side. If you pick one side, you might get positive, you'll get negative for the other side. How do we choose plus or minus? By using the convention. If it's sagging, that's positive bending moment. If it's hogging, that's a negative bending moment. There's another situation where we don't know where the bending moment is and we need to plot it. The easiest way to plot it is to plot it through the shear force diagram first and then add up the areas in the shear force diagram to plot the bending moment diagram and find the maximum. That's it. So it's doing 2 rotations. The spring is trying to rotate. I just got it all wrong.
Yeah, anti-clockwise, you make clockwise.
That was all wrong. All right. Start again. Thanks for that.
So is this is directly related to the yield point, obviously, to bend it.
This is a complete muff up. I've destroyed the entire lesson so far. Please come back. Please don't leave me.
Taking lessons.
Now that's not staying on there.
Are you doing stand-up?
You know why this... That's what it is. I've lost my brains.
This cameraman was, man.
I think we need a cameraman. Eddie, we need a cameraman. It's not working. No, one more try. I can do it. I can do it. As long as I don't fall off. You know what the problem was? I was getting left and right mixed up. All right, start again.